Hello. We're going to talk about the two independent samples T hypothesis testing situation. You should have already read chapter 16 from the book. Our scenario is a drug company claims its new drug can lower LDL cholesterol. To test this claim, you randomly gave 61 people the new drug. You also randomly gave 61 people a placebo. After 6 weeks, you measured their LDL cholesterol level in milligrams per deciliter of blood, and then some results are given. So the first thing we need to determine is what is the test situation. And so we can see that there are two samples. The 61 people on the new drug and the 61 people on the placebo. And we see that there is one variable. We measured their LDL cholesterol level. And then the level of measurement for that variable is ratio. So because we have two samples and one variable that is ratio, this is how we know that the test situation is the two independent samples T test situation. And next we need to make sure and identify our question of interest. And so we don't really have a question per se here, but it's really this claim is really our question of interest. So we know the test situation and we know the question of interest. Now that we know those two things, we can determine the hypotheses. And so when we're in a two independent samples T hypothesis testing situation, we know we're doing tests on the means. So we have these two mu's here. Now, if you're reading the book, it just does a mu1 and a mu2, which is absolutely correct, and we can write that. But I like to use different subscripts so that I remember what we're talking about. So I'm going to do an N for the new drug, and I'm going to do a P for the placebo group. So sometimes the new drug is also referred to as the treatment group, and so we could have put a T there, but something like that, and then the placebo group is there. And our null hypothesis is that these guys are equal to each other. So we're always going to assume this equality for the null hypothesis. The alternative hypothesis is we're just going to keep these in the exact same order. We're still comparing the population mean for people on the new drug to the population mean of those taking the placebo. And the mean is the mean LDL cholesterol level. And now we look to this question of interest to talk about it. And so here it says that it can lower the cholesterol. So we're going to end up with a less than here for our alternative hypothesis. So the null is always going to be of an equal sign. We're going to then look to the question of interest to determine should it be a less than, a greater than, or a not equal to in the alternative hypothesis. And in this case, because of this lower than right here, that is why it is a less than. So these are the hypotheses and symbols. Then we can just do a nice direct translation and get the hypotheses in English. The mean LDL cholesterol for people on the new drug. So all of this is the same thing as mu n. And we have equal 2, and then the mean LDL for cholesterol for people on the placebo, that's the mu p. Then we're saying we're equal to each other. And then the alternative, we have the less than right there. So as long as you can understand and interpret what mu is in the particular context with the subscript, you can write the hypotheses in English. Now that we have the hypotheses, the next step is to get the critical values. And before we get the critical values, we need to know a couple of things. And so we're going to have a delta, a degrees of freedom. And so in our case, it's going to be N1 plus N2 minus 2. And so this N1, could really think about it as N, capital N for the new drug, and N placebo for the placebo group minus 2. So that is the 61 and 61. We have equal sample sizes between the two samples in this case. So 61 plus 61 minus 2 is equal to 120. So we know that's the degrees of freedom. The next thing we need to know is the null distribution for this hypothesis testing situation is a t distribution. And so we know we're going to use the t table to get the critical values. So here's the t table. And there's a couple of things. First, when we come here, we note that 120 doesn't appear in our various delta values. So if a number does not appear in the table, you always go to the next lowest number. So we, in this case, are going to go to 100. And so we are going to be in this row. And this works anything in here where if the degrees of freedom is 55, you'd go back down to 50. The degrees of freedom is 79. You go back down to 70. So you always are going to go back down. So we're going to use this row. The question now is, which column are we going to use? And that's going to depend upon the alternative hypothesis. And so in our case, because the alternative hypothesis has a less than in it, for this reason right here is why we're going to use the 0.05 column. And so that gets us to this right here, this value. So we have this 1.660. Now also, because of this less than here, the critical value is actually going to be negative. So I use the 0.05 column because it's a less than, and I make it negative because it's a less than. When you have a greater than alternative hypothesis, you still use the 0.05 column, but you keep it positive. When you have a not equal to alternative hypothesis, that's when you would use the 0.025 column, and you then have two critical values, positive and the negative, from whatever value in the table. So the 0.05 column, because it's a less than, negative because it's a less than in the alternative hypothesis. The next thing we need to figure out is the value of the test statistic. And so we need to start using these results here. And the first thing to note is, because we're in this two independent sample T hypothesis testing situation, I know I'm going to need sample sizes for each sample. I'm going to need means from each sample and standard deviations or variances from every sample. And so this over here is just extra stuff that is useless and is there so that you're not just using the results to determine the test situation. So this information is totally worthless, and I'm not even going to look at it or consider it. That's why it's so important to determine the test situation from the number of samples, the number of variables, and the level of measurement. So before we get to the test statistic, well, let's write down the formula for the test statistic. So it's mu hat minus a mu hat all over SP and then the square root of 1 over n plus n. Now, I didn't put any subscripts yet because I want to talk about it. Now, down here in the 1 over n's, when I'm adding them together, because I'm adding them, it doesn't really matter what order it is. But I like to just always go in the same order for consistency. Now, the subtraction in the numerator matters a lot. And the best way to remember is you have your alternative hypothesis in symbols. Just always match the order of the alternative hypothesis. So I'm going to do the sample mean from the group with the new drug minus the sample mean with the group with the placebo. That order of subtraction matters. Just always match the alternative hypothesis. And so I know what most of this equals because I have the 83.4 minus, so that's new drug, and then the 102.8 is for the placebo group. And I have this big square root, and it's 1 over 61 plus 1 over 61. But I haven't figured out SP. And that's not two things. SP is the pooled standard deviation. That's what that stands for. And how you find a standard deviation is you take the square root of a variance. So the pooled standard deviation is the square root of the pooled variance. And then how we find the pooled variance is we have to use the variances. So note right here, we were given the standard deviations. So I have to convert those to variances. So S squared for the new drug group is equal to that 8.4 squared. And when you do that, you get the 70.56. And then the variance for the placebo group is that 7.1 squared. And you get 50.41. So now that I have these variances, I can calculate the pooled variance. So the pooled variance is, I'm going to take the sample size minus 1 for the new drug group, and then times that by the variance of the new drug group. And we're going to add that to the sample size for the placebo group minus 1, that quantity times the variance of the placebo group. This formula only works with variances. You always have to use variances. You cannot shortcut this and plug in standard deviations. And then we divide this by what we used as our degrees of freedom. And that was that 120. But in general, it's going to be the 61 plus the 61 minus 2. And that was 120. And so when you do this, you get a pooled variance of 60.485. Now, some things to note. The variance of one group, 70.56, and the variance of the other group, 50.41. the pooled variance is always going to be between them. So if you do this calculation, and if we'd gotten something bigger than 70.56, or we got something smaller than 50.41, we would know that we did something wrong. It's always going to be between them. And so now we can get the pooled standard deviation. It's the square root of 60.485. And that comes out to 7.777 is the pooled standard deviation. So now I can come back up here, put this 777 for the test statistic. So let's just write that one more time. 83.4 minus 102.8. So 83.4 is the mean for the new drug group. The 102.8 is the mean cholesterol for the group and the placebo. This 7.777 is the pooled standard deviation. Square root 1 over 61 plus 1 over 61. And all of that equals a negative 13.777. Now, that 777 at the end is just a coincidence. It usually will not match the pooled standard deviation. But some things to note. The pooled standard deviation is always going to be a positive value, and this square root is always going to be a positive value. So whether the test statistic is negative or positive depends only upon what is happening here in the numerator. And so because 83 is less than 102, that's why we ended up with a negative. And so we got a negative 13.777. Now we need to consider the statistical decision. And so remember our critical value, scroll back up a little bit, our critical value is that negative 1.660. So I'll draw a number line here. We've got 0, we've got negative 1.660, and my test statistic, so this is my critical value. My test statistic is way over here, negative 13.777. And so remember, because the alternative hypothesis is a less than, I'm going to reject in this direction. So this is where we would reject the null. And this is again coming from this alternative hypothesis. So I would say reject the null because negative 13.777, the test statistic is less than negative 1.660, which is the critical value. So my statistical decision is to reject the null hypothesis. Now we skipped one thing, so let's make sure we come back to that. Run out of room here. And that was the probability statement for the p-value. And so the p-value is going to be the probability of, well, what was the null distribution? It was t. We're going to do less than, because of the alternative hypothesis, the value of the test statistic. And we don't use any absolute values because we're in a less than. We only use the absolute values in a not equal to alternative hypothesis. Now, this is the same thing as saying 1 times the probability of this statement. And the only time we would multiply by 2 for that probability statement is in the not equal to case for the alternative hypothesis. So because it's a less than, that's why we have a less than right here and why we multiply it by 1, which is just the same thing. So that is the probability statement for the p-value for this scenario. And we decided to reject the null hypothesis. And so now we can get to the conclusion. And so I first am concluding that, and when I look here to here, that is the alternative hypothesis in English. So that's the first thing. We rejected the null hypothesis, so we're going to conclude the alternative. So really, we said less than. So if somebody said, hey, I conclude that the mean LDL cholesterol for people on the new drug is less than the mean LDL cholesterol for people on the placebo, you'd follow that up with, well, how much less is it? And that's where the specifically part comes in. And what we're going to do is if you take 83.4 minus 102.8, so this is mu hat for the new drug minus mu hat on the placebo, you get a negative 19.4. So we're not using this 19.4. We're taking the mean difference and we're interpreting that. And so we would say specifically, I predict the new drug will lower LDL cholesterol by 19.4 milligrams per deciliter. So the lower, because it's a negative value, and then we're talking about how much it is. So in the conclusion, we're saying it's less, and then we're interpreting or giving our prediction by how much we would predict it to be less. And that's the 19.4 milligrams per deciliter.